All right, this is Unit 6 progress check. Free response part A. So we're looking at number 1, and it mentions that no calculator is allowed for this question. So I am saying everything that I'm saying under the assumption that you are looking at the problem in front of you already. So I'm not going to keep copying down. I might put them in front of the camera from time to time, but I'm not going to copy every little thing that's on this paper because I am assuming that you are already looking at it. So we have a table. The table is given in time in hours and then a rate in gallons per hour. It's the rate at which water leaks from a container. And we have 4 different values in this table. So we're going to start with letter A. Letter A asks us to find an approximation for R prime of 1/2 and then show the computations that lead to your answer. So R prime is a derivative. A derivative is a slope. And so if you're looking at a table would just be like a regular algebra 1 slope, like change in y over change in x, or in this case it'd be change in r over change in t. So you want to get as close as you can to those points. So 1/2, the closest you can get is to use 1/3 and 2/3. So we're going to do just the slope between 1/3 and 2/3. So our computations, we'd say this is approximately, and then we do the rate at 2/3 minus the rate at 1/3 over the change in t, which would be 2/3 minus 1/3. You want to make sure you're showing this work and not just randomly plopping down numbers that come off the table. You want to show what you're pulling off the table before you write it down. So the rate at 2/3 is 5 gallons per hour minus the rate at 1/3, which is 8 gallons per hour. And then when I subtract these, I get 1/3. Keep subtracting, I get a -3 divided by 1/3, which would be times 3. So that comes out to be a -9. And then our rate, so R is given in gallons per hour, and then that would be per hour. So it's kind of like an acceleration sort of unit, like a meters per second per second. So this is gallons per hour, which means the rate is decreasing at -9 gallons per hour Okay, so that's part A, indicate units of measure. We got those right there. Letter B. Letter B says use a left Riemann sum. Remember what I've been telling you guys in class. It's never going to be your idea to use a Riemann sum. They'll always tell you, and they'll always be specific about which one they want you to use, whether that's left, right, midpoint, or trapezoid sum. So 3 subintervals indicated to approximate this value right here. So these are the values of t, starting at 0, ending at 1. We've got 3 subintervals on the table, and then these are the values that we use as the height. So our left Riemann sum, we'll put the table up here for right now. So our first interval goes from 0 to 1/3, and for the left, we're going to use this value right here as the height, because between these 2 points, we want the left end point. So from 0 to 1/3, that would be a width of 1/3, and then what we're going to write is times R of 0. Just like up here, you don't want to just start randomly pulling things off the table. Plus, and then the next interval goes from 1/3 to 2/3. That would be, again, a width of 1/3. This time, we're going to use the value at 1/3, which would be the left bound of this rectangle right here. So 1/3 again for the width, and the height would be the rate at 1/3. Plus, and then one final rectangle would be the last interval from 2/3 to 1. Again, a width of 1/3. Since it's a left Riemann sum, we're using the rate at 2/3 hour. So we write this down first because we want to make sure that we are showing the computations that lead to our answer. And we have 1/3 times R of 0, which is 11, just pulling that off the table. 1/3 times R of 1/3, which is 8. Plus, and then 1/3 times R of 2/3, which is 5. This is a non-calculator section, so just so you guys know, on the actual AP test, if it's just a string of numbers, you can feel free to leave that as your final answer. Make sure that you indicate units of measure, just like it says. I'm going to get an actual answer here. All right, so I add these all together. 11 and 8 is 19, plus 5 is 24. Thirds would be 8, and our units, if R is given in gallons per hour and then I integrate it, it becomes gallons. Remember, when you integrate a rate, you end up with a final amount. So our approximate value would be 8 gallons during that 1 hour time period. All right, so that was part B. On to part C and D, the next part of this problem. On the back of this page says, use the data in the table to evaluate this right here. So from 0 to 1/3, R prime of t dt. So now notice here, it doesn't say approximate. It says evaluate. Evaluate means that's an exact answer. We can actually find this. So for approximations, we use Riemann sums. For evaluations or exact answers, we use either the fundamental theorem, or if we have like a perfect geometric shape, we could do area under the curve, okay? We don't have a graph. We have no idea if it's a perfect geometric shape, so that leaves fundamental theorem. And the way fundamental theorem works is you take the antiderivative, plug in the upper bound, plug in the lower bound. So the antiderivative of this would be just r. So antiderivative is r. We evaluate it from 0 to 1/3, and we can plug those values in. This is how the fundamental theorem works. We plug in the upper bound, we plug in the lower bound, and subtract. Okay, so coming off of that table, r of 1/3 is 8, minus r of 0 is 11. And we subtract that, we get -3. The units there would be in gallons per hour because those are R's units and we're just pulling values of R off the table. So think of this as a net change. That's exactly what we did in section 5.5. This R prime is a rate, and so I integrate that rate and I get the net change of that quantity. So I get the net change in R, or how much R has changed over that time interval. This is how much the gallons per hour, the rate at which water is leaking, that's how much that rate has changed over this 1/3 of an hour or 20 minutes. All right, last part, part D. It gives us a sum right here. So that I am going to copy down because we know this formula is a little complex. So I want to make sure that I'm putting kind of the generic formula in front of you and then comparing it to what we have here. So our generic formula is this. Well, we normally have a limit out here, so they mention that part. It says the sum is a right Riemann sum, and then it says the limit of this sum is the definite integral. So here's what we normally have as the definite integral. Inside the sum, we write f of a plus the change in x multiplied by k. And then on the outside, we multiply that by the change in x. So what that ends up equaling is a definite integral, just like part D says, and it's this definite integral right here. So one other thing to put in a definition is that delta x is always defined as b minus a over n. So just looking at this, we're going to be able to gather up a couple of things. One thing that we do know is that b minus a is equal to 1. Okay, so that's one thing that we can get off of this information. B minus a is equal to 1. This value right here, the first thing you plug into the function is your value of a. So that right here is a 1/4. So we know that a is equal to 1/4. So then going right back to this, if b minus a is 1 and a is 1/4, that must mean that b is 5/4. So now we have our integral. So let's at least start with that. So our integral, we have from 1/4 to 5/4. Those are our bounds. And then we have this 2 right here, that's actually supposed to be part of our delta x. Let me backtrack a little bit. So the 1/2, normally there's only an n in a denominator, so that means b minus a must be 1/2, my apologies. So if this is 1/4, this must be 3/4, because our change in x would be 1/2. So half a unit away from 1/4 would be 3/4. My apologies there, I missed that too when I was first looking at it. So 3/4, and then in our integrand, here's f, here's f. So this is r of, and we can just assume that it's an x, or we can stick with the variable they've been using and use a t. It really doesn't matter. So let's use that as a t, and then dt. So that is our expression. If we pull all the right pieces, figure out what delta x is, figure out a, figure out b, that would be this definite integral. And I am going to separate all 3 videos just in case you only want to watch one. So this is the end of part A, number 1.